Good morning all. Today I'm going to be working on this, or should I say these. I have two of my tiny little PWM5 Femto V2s. This is the world's smallest solar charge controller, unless you can tell me otherwise. Now I did attempt to do some filming of me soldering the components onto these two boards, but unfortunately the footage was hampered by the fact that you've got to get extremely close like this. Well, if I'm this close with the camera, which is only a couple of inches away, I can't actually get my soldering iron in. The other thing was that soldering this stuff meant lots of expletive filled monologue, and so that really couldn't be shown on my channel. But these are done, and we'll get some close-ups courtesy of the magnifying glass. Ooh, yes. Now you can see some of the components are a little bit wonky. That's to be expected because I can't see what I'm doing. Regulator there in the bottom right corner. The tantalum capacitors are all a little bit wonky. Let's flip this over to the other side. You can get the microcontroller reasonably straight. That's not too difficult. In fact, the two hardest components are those dual diodes at the bottom of each board marked A1 and A7, and that's only because, I mean, it's a standard SOT23 package, but the pads for those two components are extremely tiny, which helps them fit on the board, so that's a good thing, but it makes soldering extraordinarily difficult. If you look at the SOT23s on the transistors on the other side, the pads are much more elongated, and therefore you've got a much better chance to get those things on, well, because your pad's bigger. So these boards are done. They're missing two components, the MOSFET and the transient suppression diode. They're both through-hole components. So far I've only put on the surface mount. But even without those two components, these boards will do something, and I can actually test them right now with a 12-volt battery. So I'm going to use this 10-pack of Eneloop lights. Now I know, let's get in a bit closer, I know that the triple pad adjacent to the microchip there are all 0 volts, and it's not going to focus, is it? Oh, it has. And this point here on the MOSFET, the source, takes 12 volts, so I can poke my wires in and actually get this to do something. So let's do that right now. Poke negative into there, positive into there. There's the boot light. There's the sort of pulse width modulation that backs off, probably due to the capacitor on the measuring circuit. Oh no, it's actually probably due to the stepping in the microcontroller software, because it steps back at a linear rate, and so it had to unwind from 255 all the way down to 0. Anyway, don't worry about that. What it's doing now is it's flashing out 1, 2, 3. One, two, three, like that. Oh, 123.1. So this is now saying that the batteries are at 13.1. Well, they may or may not be. Let's try the other unit. Whoopsie. So let's put that one in negative, that one in positive. Boot up light, backing off of the PWM to 0 PWM. No, 100 PWM. Yes, it's a forwarding of the PWM, because 13 point... No, what did it say? 1, 2, 3, 1, 2. This one is measuring slightly different to this one, and that is entirely... I've got to be careful here. Let's take it off. That's entirely down to the regulator, because of course the A to D converter in the microcontroller is referenced to 5 volts, and these regulators are going to have slightly different versions of 5 volts. One's obviously a little higher than the other, and therefore they're measuring slightly differently. It doesn't bother me too much. The precision on this doesn't need to be wildly accurate to charge a thumping great lead acid battery. So this one is saying 13.2. Now 13.2 is less than 13.5. That's the target voltage for charging up the lead acid battery, if indeed this were a lead acid battery. It isn't. So at the moment, the microcontroller has its PWM wound right up to 100%. So if I connected some solar into here, which would be on that middle pin, drain, the MOSFET would turn on 100% and the solar panel would charge the battery until it gets to 13.5, at which point PWM would kick in and it finds a point within the PWM range. We can call it 0 to 100%. Somewhere within that range, the battery will be held at 13.5 volts. So this means that these two circuits, I think, are working. Now another test I can do, if I power this up with these two wires, is to check whether the microcontroller is generating 20 volts. It does that by waggling two pins, and there are two capacitors. Where are they? Yes, here under the back, and three diodes, and it's in a voltage multiplier configuration. So that should be generating 20 volts. Now I can pick it off on the positive of this tantalum. So let's just try picking that off. And that's saying 7.7 volts. I've got a feeling I've just put my negative, which I've put here, on the wrong clip. Yes, I have put it on the wrong clip. It should be on this clip. Yeah, that's more difficult. But I think I can probably shove that in there. That's negative on the battery, not that one. That was positive. So let's try again. Negative to that point. Positive to that point. Get that thing so that the LED's lit up, and try and pick off this voltage. And there it is, 20 volts. So the step-up generator, the voltage multiplier is working. We've got 20 volts. Now that's used, of course, to drive the MOSFET gate. I should just test that on the other unit. Let's do that. Pick it off on this upper corner. And there it is, 20 volts. So those two boards, I'm satisfied, are working. The microcontroller is running, it's doing its basic voltmeter function, and it's generating the high voltage for the FET. Now I guess it's time to put the FET in and the transorb, the transient suppression diode, and attach the wires. And I've been gathering together various parts for this. So I've got my pin connectors. Now these pins, when I attach the wires to these boards, I can force these pins up into the ends of the wires, which means I can do some set point testing, some target voltage, some float voltage testing, so that when my lead acid battery gets up to 13.5 volts, we'll see modulation on the LED. So let's get my lead acid battery that I'm going to use for testing. And that's this. I've got a couple of these 6 volt 5 amp hour ProElec lead acid batteries, so they're separate. I've linked them together. Doorbell. Electricity meter reader, all done COVID style. Yeah, so two of these ProElec 6 volt 5 amp hour, which I did buy for my Maplin heaters, but they're pretty pathetic, so they're actually probably more use to me as just 12 volt test lead acids. And of course, being 6 volts, I was able to put a fuse in the middle, which makes life nice and easy. So what I will do is charge these batteries through that. I'll need a male-to-male adapter to go into there, and then I can push these pins into my charge controller wires. Now, another important item for these two charge controllers is in this box, so let's get this open. I'm pretty sure these are the clear plastic fronted enclosures. Yeah, and these I think are the right ones because they've got the flanges. That's very important, so I can screw that to the fence, and the plastic fronts. And this enclosure has proved to be excellent for the existing charge controller. Now I can make 2 more. I'll have all 3 of them. And it's the PWM5, which is my own solar charge controller design. So that's at about 12.3 volts. Other things which I'm gathering, the two MOSFETs, oh they are the right ones aren't they? IRF3205, that's right. The two transient suppression diodes with the 33 volt threshold for when they go dead short to take out transients above 33 volts. That just sits across the solar panel side of this thing. In case you've got long solar panel wires and induced voltages from nearby lightning strikes could create a high voltage, these clamp that out. The wires, they've been sitting in straight fluted plastic for, I don't know, a couple of years, so they've probably had 600 temperature increase and temperature decrease cycles, so they're quite straight now. Actually, that curve from being on the reel is starting to just creep back in, isn't it? Interesting. What I want to find now is something to use as a dummy solar panel. There's not really any sun and it's cold outside, so I'm going to find a 12 volt transformer based linear power supply. They behave a little bit like solar panels, good enough for doing the test from solar panel through the charge controller into the battery. And finally this thing, which is a transformer based power supply. It was for an LED work lamp. It's rated at 12 volts 500 milliamps, obviously mains on the input. Now I've just put this in the mains, measured what's coming out of this plug, and it's actually 18.5 volts, so it's very high, and then it gets pulled down by the load. Well, this mimics a solar panel quite well. So when I connect this through the solar charge controller to the battery, remember the solar charge controller at that point is 100% on, so the battery will immediately pull the output of this down to whatever its voltage is, probably about 12.5 at the moment, and then of course this will start receiving charge and that voltage will come up until it gets to the set point of the controller, which is 13.5 volts. Sometimes it's 14.4, it's got a boost mode. And at 13.5 volts, of course, this thing will start to modulate and the battery voltage will be held at that voltage, and then it will just absorb charge at a fixed voltage, but more charge will come in and accumulate inside the accumulators. Next thing I need to do is I need some contact points. I'm going to break these apart actually. They don't need to be one piece anymore. I need some connection points to connect all my wires. Yellow for incoming solar, 2 lots of black, red for outgoing, I suppose, to the battery, but of course it's also incoming to keep the microcontroller circuit running. So what I need to do is bend this to a suitable shape. Let's bend it such that 33 sits at the top so you can at least identify it. That should be about right. It needs to fit across these two outer holes, but before I can put that component in, I need to fit a little link, which I'll use a cut off of the leg, across those 2 points there, which sit actually underneath this thing. So this thing sits on top of that. So I'll cut one of these legs off with enough left over still to use this component. Now, can I bend this with a flat on it so that it sits nicely across the 2 holes? That looks pretty good. Sits across these 2 holes. Now, MOSFET goes there, so all these through-hole components will sit on this top side. Push that in and down, and then I can solder it and bend these legs. Now, these legs I'm not going to cut off, because they are what my wires are going to solder onto. Okay, let's make my first solder joint. Clean the iron. Sponge isn't quite wet enough. So what I'm doing is I'm soldering in this link. Sorry, I can't get the camera any closer really, otherwise I wouldn't be able to solder. Soldering in this link. That's enough, don't need a big bulging mound on there of solder. And then those bend in opposite directions, that's right, because one black wire goes one way and one black wire goes the other. And now I need some anchor points for the red and yellow wires, and they are 2 of the legs of this MOSFET. The gate leg gets cut off, But source and drain are the wires yellow and red. Drain is yellow, red is source, and provide the points to connect these wires. Because this board is so tiny, 1 inch by half an inch, there's no way I could have put connection points on there. So the wires connect directly to the through-hole component that does the switching. So now I'm soldering in the transient suppression diode. Yeah, that's not soldering too well. Oh, that's probably because that's a ground point. So let's boost the temperature on here up to 420. So I can get that soldered. And the other side probably won't need the boost because it's not a ground point. Although I don't think I've got ground planes on this. Let's have a closer look at that. And there it is. So the two wires in the middle are my connection points for the black wires. The two wires on the outside, of course, are the transient suppression diode with its 33 volt rating. And they will be trimmed off. I'm just going to go and get my trimming cutters. There are only two through-hole components to go on here. So I've done the transient suppression diode. The next one is the MOSFET. I'm going to bend the legs right flat against the body of the component. Both of them, of course. I'm doing two of these charge controllers. And let's get those, well, into the board. So it sits in like that. Now the body of the MOSFET just about sits within the edge of the board, not including the tag. The tag could be taken off, but it would be quite mechanically invasive to do that. So I'm just going to leave it on. It doesn't really matter. This is going in a relatively large box. The fact that it's the world's smallest solar charge controller is not really an issue at the moment. I'll get that soldered in. Right, I will do gate, which is that one. If I can get the solder onto my iron. Source, no, drain, which is the middle one. And source, which is that. What just went da-da-dum on my phone? Why is that? It's plugged in. Now I've got to be really careful now. There is a guide actually. It's this pin I need to cut off. This is the gate. If I flip this over, gate's on the left of a typical MOSFET. So that's the one that comes off, and that leaves me with this staggered arrangement. The two in the middle will be, oh, what would they be? Well, these two are ground, of course. These two have the black wires. Yes, that's right. This one will head off in that direction, having cut off this gate leg. Let me do that now, actually, and then it'll be more obvious what I'm doing. So be very careful here. I get the right one. Cut off the gate leg. So now this black wire will go up, so that'll be black for solar panel, and drain will go up. The drain actually is the middle pin, and that's connected to the tab, so you could use the tab, I suppose. That'll go up to solar panel, that'll be yellow. This black will come down, that'll be black for battery, and this one on the source of the MOSFET will come down, that'll be red for battery. So you'll have battery one end, solar panel the other. So those four wires do not cut, otherwise you have to start all over again. And now I bend these, so a ground goes upwards, a ground comes downwards, the source of the MOSFET goes upwards towards the tab, no, that's the drain, sorry, which is also the tab. The source comes downwards, and so there's my battery connections and there's my solar panel connections. Let's strip and tin some wires. Okay, stripped wire, let's tin it. It looks slightly tarnished, the copper inside this black wire. Don't quite know why. Maybe it's an older reel. The copper inside the yellow and red just seemed to be brighter. Right, now let's tin the ground, which is this one, or one of the grounds, and get it with a little blob so there's enough solder on there that I now don't need to add solder when I link these two together. And I can't quite remember how I used to do this. I think I ran the iron across the top, and the important thing is, I'm watching from the side, you're watching from the top, to sweep up and down, that's it, to get really good connection between those 2 points. I'll come in really close on that. So you can see, I hope, how the black wire now hasn't totally enveloped the copper leg that I put through the hole, but it's a really good long connection there onto the top of that, so that should be good enough for the high current. It's about 5 amps max that's going to flow through that connection, and then I'll put a heat shrink piece over that just to make sure nothing sort of connects to anything else. Let's get the remaining wires on. Tin the red wire. Yeah, definitely brighter copper. Right, a little bit of a bulge on there, so we've got a bit of surplus solder. Oh, now I should have done the red first because it's behind me now. It's a bit of a problem, so I'm going to turn this round and do it from this side. Don't want to melt that wire. Which one am I doing? Oh, one thing I've noticed is that black wire has sort of rolled over this way, and it's very close to the red. So we'll need some careful insulation between these two to make sure that they don't short together, because that wouldn't be good, shorting the battery connections. In fact, I'm going to take this black one off because it isn't where I want it, and it is in the way of the red one, and I'll put that back, I think, once I've got this red one on. So let's do this one first, and this time I want to try and sit it centrally on top of this leg. It's hard to see what you're doing, of course. That looks better. Now the black one can go back on, and I will do the other one in sequence, back to front. Silly doing the front one first. Ah, it's moved! So a close-up of those two soldered on wires, and I hope you can see now that they are good connections with the wire coming out of the circuit board, or the leg coming out of the circuit board. They're nicely separated, so they sit next to each other nicely. So that's red and black for the battery. I'll get their heat shrink pieces on. So I keep a tray of pre-cut sort of 1/2 inch lengths of yellow, black and red, just for these sorts of things. And also I use these a lot for when I solder the crimp terminals on, which actually I'm going to have to do because I'm going to have to put a couple of ring terminals on that end so that this thing can connect to my big lead acid battery outside in the garden. So just before I heat shrink all this sleeving, I just wanted to do a close-up of how this all connects. Red and black on the right are my battery connections. Yellow and black on the left are my solar panel connections. Yes, they're all pretty close together, but then this is the world's smallest solar charge controller. Right, let's just slide these heat shrinks up and find my heat gun and shrink it all. Right, I'm going to use the 18 volt Ryobi heat gun for this, and if you think 18 volts would make an underpowered heat gun, no, it's awesome. I can't direct this heat very well, so it is going to make the board hot. I think that's got it. Let's take a closer look. And there it is. So what I can do now actually is, I hope this isn't too hot, just press these a little bit flatter against the board. Oops. Like so. And that should be good with no shorts or problems like that. So the next thing is to test it on my low current apparatus. My two lead acid batteries have a 5 amp fuse in them, and my dummy solar panel is only 500 milliamps. And this is where I'll get these pin connectors and push the pins up inside the wire ends. I'll lay it all out on the bench and we'll have a look at that. And here are the two charge controllers with their wires on. So the next stage is to test them. And like I say, that involves pushing these pins up into the ends of the wires. The reason I came up with this idea, I don't really need to do it now. I could strip these and connect them into these. But when these were shipped to customers, when I was manufacturing these, I wanted to test them in such a way that was non-invasive. I didn't want it to look like... I suppose I could have put these in a block and then cut them a little bit shorter. But I just came up with this pin idea and it worked quite well. So there they are. Next is the testing. I might leave that to another video, I'm not quite sure. But I want to fully test them on a sort of low current setup. Now, of course, the black and red wires will go down to 2 ring terminals, straight down to the big Trojan batteries, which are capable of massive currents. The fuse idea, I'm just very uncertain about. I'm just not sure whether a fuse would actually help. I'm not sure it would have helped the charge controller that's out there that's all blackened and burnt. I'll probably do a video on that at some point. We'll get close in and have a look at that. So I'll probably not go for a fuse. I haven't done a fuse on the one that's out there currently working. I think as long as these are sitting in their enclosures, these things, they're not going to get corroded, and we're not going to get the problem of 2 points creeping together and then an arc forming, which is what I believe caused that other one to burn out. But yeah, for the moment, these are done. That's probably it for this video, so cheerio.